In this video lecture, we'll be solving this problem, cheapest flights within K stops, which is a LeetCode medium problem. In this problem, we are given a network of flights and we have n cities connected by these flights, and we are given flights array where each element in the flights array is a tuple of integers representing the starting city, the ending city, and the price to move from the starting city to the ending city. So there is a directed edge from the starting city towards the destination city. Also, we are given three integers: src representing the source city or the starting city, dst representing the destination city where we want to reach, and an integer k which represents the maximum number of stops which are allowed in the route from the source city to the destination city. If there is no such route, then we have to return -1. In the input, we'll be given flights array containing n tuples, a source city, a destination city, and an integer k representing the maximum number of stops which are allowed. And in the output, we have to return an integer representing the cheapest price to move from the source city to the destination city with the number of stops allowed as k. Let's better understand the problem statement using an example. So here we have our network of 4 cities. They are numbered from 0 to 3. The source city is 0 and the destination city is 3, while the stops which are allowed in the route from source to destination are 1. So let's see the number of routes. Let's see the different routes to move from city 0 to city 3. One of the routes would be to move from city 0 to city 1, then from city 1 to city 3, giving us the cost of 100 plus 600, that is 700. And we can see that the stops in this route are 1. So there is only one stop in the route from 0 to 3. Let's see another route to move from 0 to 3. You can see that we can move from 0 to 1, then from 1 to 2, then from 2 to 3. And the cost along this path would be 100 plus 100 plus 200, which is 400, which is the minimum cost. But we can see that the number of stops in this route are 2, that is 1 and 2. Hence this route is not allowed because k is given as 1. We can have at max 1 stop along the optimal route. So the answer for this test case would be 700. That is, the cheapest price to move from city 0 to city 3 is 700 units. Fine. So let's see how we can solve this problem. So consider this graph and let's try to build the solution for this problem. We can see that this is a directed weighted graph and we want to find the shortest path to move from the source city to the destination city. So in this case, the source city is city number 1, the destination city is city number 3, and the number of stops allowed are, so we are allowed to stop at 2 cities while moving from the source city to the destination city. So let's see how we can solve this problem. So we want to find the shortest path to move from this source city to this destination city from 1 to 3. If it would have been a unweighted graph, in that case I would have used BFS search, because we know in BFS strategy, whenever we visit a node first, then the cost to reach that node will be the minimum cost. So let's say I start my BFS from node number 1 and I reach 4 along this path, that is moving from 1 to then 4. In that case, this will become my shortest path and with the cost of 2, in case the graph would have been unweighted. But this is not the case here. We have a weighted graph, so we cannot use plain BFS. So how would I modify my BFS if it can work for this problem? We can observe that we have a bound k here. So that means along the path from source to destination, we are allowed to stop at 2 nodes. That means if I consider the starting city as level 0, so let's consider this as level 0. I will explore all the adjacent nodes of this node, which is node number 1, which are node 2 and node 3, and these I will consider at level 1. Then I will explore this node, which is node number 4, and I consider this as level 2. Then in the next level, which would be level number 3, and in this case that level would be this. So this would be level 3, and what I am claiming here that I would find my destination city when I reach level 3. So I can stop my BFS search when I have crossed these stops. So when I have covered 2 stops, then I can stop my BFS search. So I have covered the source city, I have covered this level, which is level number 1. Then I have explored the level number 2. So whenever I reach level number 3, I can stop my BFS search, and that level, which is k plus 1, would be the last level to explore, because at any level which is greater than k plus 1th level, I'm sure that I will not find my destination city, because at that level I would have explored more than k stops. That route would not be possible because I'm allowed to stop for at most 2 cities. Fine, so that's the idea. So that gives me an upper bound to run my BFS. Therefore, I can use my BFS search for this particular algorithm with a little modification. So let's see how BFS algorithm will work for this problem. We have this source city, which is city 1, destination city, which is city 3, and maximum number of intermediate stops allowed are 2. And we initialize our stops variable to 0, and we initialize our queue with the source city along with its distance, which is 0. Then we have our distance array, which we initialize with a very large number. So we initialize it with infinity. So infinity is, take it as a very large number, let's call it int max. Then I run my BFS and I explore the only node which is present in the queue, which is node number 1, and I move to its adjacent node, and which are node number 2 and node number 3. This corresponding pair for these nodes would be 2, 10, and for city 3 it would be 3 and 50. I can see that. So the distance for city 1 is initialized to 0 because I'm starting from this city. Then I can see that the distance 10 is better than the distance which we already have for city number 2, that is infinity. So I replace this infinity with the distance 10. Same goes for city number 3. The distance till city 3, which is 50, is better than the distance which we already have for this city, which is infinity. So I replace this infinity with 50 and I push these pairs into my queue. Okay, so this is how, and the number of stops is updated to 1. That means we have to explore at least 1 stop before I reach my destination city. Either I move to the destination city through node number 2 or through node number 3. I have to explore at least 1 intermediate city, either city 2 or city 3. Fine. So that's what I am saying here. So stops variable is incremented to 1. Then I pop this node number 3 out of the queue and I move to its adjacent nodes. But we can see that there is no adjacent node for city 3. So it stays as it is. I simply pop it out of the queue. Then I explore node number 2 from the queue. So I pop node number 2 from the queue and I explore its adjacent nodes. And there are 2 such nodes, which is node number 3 and node number 4. And I can see that to reach node number 3 while passing through node number 2, the distance would be the distance for node number 2, which is 10, plus the distance to move from node 2 to node 3, which is 30. That would give me 10 plus 30, which is 40. So the new distance is 40. So what I'm saying here, to reach the city number 3, I take 40 units of price. Is it better than the already existing distance or price which we have for city number 3? And the answer is yes, because we have 50 for the city number 3 along this path. While along this path, the distance becomes 40 or the price becomes 40. So I update my distance array for this node. So it becomes 40. Fine. So this is how I'm performing my relaxation here. Then I again push the city number 3 into the queue, and I also have to push the city number 4 into the queue, and the pair for city number 4 would be 4 and the distance would be 10 plus this 10, which is 20. Fine, because I'm exploring the adjacent vertices of node 2, and to reach node 4 through this vertex I have to pay a price of 10 plus 10, this 10, that is 20. So I update the distance array for node number 4 because 20 is better than infinity. So I replace infinity with 20 and I push this node as well. Fine. So we have explored city 4 as well. Now I pop the city number 4 from the queue and I move to its adjacent cities, which are city number 3 and city number 5. Then I explore the city number 3, and we can see that there is no adjacent node for this city. So I pop this out of it. Then I explore the city number 4. So notice that the stops variable becomes 2 here. So after I push node number 4 and node number 3 into the queue here, the stops variable has become 2. That means if I reach the destination city through the node number 4, that means I have to explore at most 2 stops. Fine. So this variable has become 2 and k is given as 2. So I cannot explore the level number 3. So I cannot explore the next level, which is level 3. I have to find my destination city at level number 3 because the stops variable has reached the limit. Fine. So I pop this city 3 out of the queue, and I can see that there is no adjacent node for city number 3. So I pop it out of the queue and I update the distance which is given here in the distance array. I can see that this is 40 and the distance that we already have for node 3 is 40. So there is no need to update it. Then I pop the city number 4 from the queue and I explore its adjacent nodes, which is node number 5 and node number 3. These will be at level 3. So this will also be at level 3 now. So explore the city 3 and the corresponding pair for city 3 would become 3 with 20 plus 15, which is 35, because I am arriving at city number 3 through city 4. And to reach city 4 we have distance as 20. You can see that from this distance array, and the price to move from city 4 to city 3 is 15. So 20 plus 15 gives me 35. So I update my distance array because for city number 3 the distance which we already have is 40 and 35 is better than 40. So we update 40 with 35 and I push this node into the queue. So I push 3 with 35. Then I explore city number 5, and to reach city 5 the distance taken would be 20 plus 5, which is 25, and 25 is better than infinity. So here I replace infinity with 25 and I push this pair into the queue. 5. Fine. While the stops variable will be incremented to 3. Then I stop my BFS right here because I have exceeded the number of stops which are allowed. So there is no meaning to explore this next level which is present in the queue. Fine. So I stop my BFS right here. Then I return the distance of the destination node which is present in this destination city, which is present here in this distance array, and that distance is 35. So the answer for this particular test case would be 35. The most optimal path to move from the source city to the destination city, that is from 1 to 3, would be to move from 1 to 2, then from 2 to 4, and finally from 4 to, with a cost of 35 units. So this is the cheapest price which we require to move from source city to the destination. So that's how the algorithm works. That's how a little modification in the BFS will do the job. Let's see the implementation for the idea. Okay, so here is my find cheapest price function which takes in the flights array, source city, destination city, and the upper bound for the stops. I declare an adjacency list which will be used to store the graph. I prepare my directed graph here. I declare a distance array. I resize it to n. I initialize it with a very large value. Then I declare a queue and I push the source city along with its distance into the queue. I declare a stops variable and initialize it with 0. Then I run my BFS search while the stops are less than equals to k. So I'm putting a upper bound here. That means I'm not allowed to visit stops more than k. And the queue is not empty. Till the queue is not empty, I run this while loop. I calculate the size of the queue. And for all the nodes which are pushed inside the queue, I pop the front node, its distance from the source city. Then I move to the neighbor nodes and I check if there is a scope for the relaxation. That means if the price to arrive at the neighbor city through this node is lesser than the price which we already have for that neighbor city in our distance array. In that case, I perform my relaxation and update the price in the distance array. And I push this pair, that is neighbor along with its distance, into the queue to explore it further. Fine. So that's how I explore all the nodes at a particular level. Then I increment my stops variable by 1 after I explore a certain level in the graph. And finally, at the end I check if the distance to the destination city, if it is same as it was initialized, which is a very large value, that means I haven't arrived at the destination city. That means I haven't arrived at the destination city through any path. And in that case, I will return -1. Otherwise, I will return the distance to that city. So that's how the algorithm works. Let's see the code implementation for this idea. So here's my solution class, which has a find cheapest price function, which takes in the flights array, a source city, a destination city, and the maximum number of stops allowed. I declare an adjacency list to store the graph, and I prepare my list from the given set of flights. Then I declare a distance array along with a queue. I initialize the distance array with a very large value. I initialize the queue with the source vertex along with the stops to 0. Then I run my BFS search while the stops is less than equals to k and the queue is not empty. So this puts an upper bound to the number of stops which can be explored, and I calculate the size of the queue to explore a certain level, which is denoted by the number of elements which are present at that queue. So at level 0 we have source city only. I explore all the nodes which are present in the queue, and here I am checking if it is better to arrive at the neighbor node through this current node. If it is the case, then I perform the relaxation and I push the neighbor along with its new distance into the queue, and I increment the stops by 1 till it exceeds. So I run this loop till the stops exceeds k or the queue is not. Finally, I check if the destination city can be reached. If it cannot be reached, then I return -1. Otherwise, I return its cheapest price from the find. So that's the implementation in C++. That's the implementation in other languages. So this is the implementation in Java, and this is the implementation in a Python language. So that's all for this video. If you like the video, then hit the like button and make sure to subscribe to my YouTube channel and give your feedback in the comments below. I will see you in the next video. Till then, take care. Bye bye.